Okay, in this lecture, we're going to cover the section 2.8 material on exponential growth and decay. So now that we've taken a look at differential equations and separable differential equations, we can take a more detailed look at the section 2.8 material on exponential growth and decay. So to introduce the exponential growth model, let's consider the following example. Suppose that y of t is used to denote the population size of some species at a given time, t which is non-negative. So in the exponential growth model, we will assume that the population changes at a rate proportional to the population size. So that is the rate of change of population size, or the derivative of the population size function with respect to time, is some constant multiple of the population size y. So the rate at which the population size changes is directly proportional to the population size itself, where r is some positive constant called the growth rate, or sometimes intrinsic growth rate, of the population. And we have some initial condition, y at time 0 is a known value, y naught, which represents the initial population size. So in part A of this example, we are asked to solve this exponential growth model. So what we have is the differential equation dy dt is equal to r times y. So this is a separable differential equation, which we can solve using separation of variables. So here, if I separate the variables, I would have dy over y is equal to r dt. And to eliminate the differentials, dy and dt, I can integrate on both sides, which would give me the natural log of absolute value y is equal to r times t plus c. As a reminder, we're grouping all of our constants of integration on one side of the equation. So to solve for y, I can exponentiate on both sides. So I would have the absolute value of y is e to the rt plus c power, or as we had seen in our section on separable differential equations, we can rewrite the right-hand side of this equation using properties of exponentials as e to the c times e to the rt power, where this e to the c term, since c is an arbitrary constant, is just some new arbitrary constant. So I can write this as the absolute value of y is equal to some constant, let's just call it c again, times e to the rt power. Now to solve for y, I need to eliminate the absolute value. So here y as a function of t, if the absolute value of y was c e to the rt, that means that y would be positive or negative c e to the rt. And again, since c was an arbitrary constant, it doesn't matter whether I have a positive c or a negative c, because the positive or negative of an arbitrary constant is just a new arbitrary constant. So let's write this more simply as y of t is some constant c times e to the rt power. And we now need to find the constant c that satisfies the initial condition we had, where y of 0 was equal to y naught, which was our initial population. So applying that initial condition, we have y of 0 is equal to, if I substitute 0 in for t In the general solution I just had, I would have c times e to the 0, which is just c. And the initial condition from the problem statement is that that has to equal y naught, the initial population size. So substituting that value of c back into the general solution, we have y of t is given by y naught, the initial population size, times e to the RT power. So this is the solution of the exponential growth model. It says underneath this assumption of exponential growth, that is where the rate of change of the population size is proportional to the population size. The population size at any time is given by y of t equals y naught e to the RT. So that is the initial population size y naught times some exponential factor e to the RT, where r is a positive constant referred to as the growth rate or intrinsic growth rate of our population. Now, in part B of this example, we're asked to determine the limiting behavior of the population as time t approaches infinity. So after a very long period of time, what will happen with our population size? And then we ask the question, does this seem realistic? So here we could say, well, as time t is approaching infinity, let's consider the limiting value of our population size, y of t. That is the limit as t approaches infinity of y naught times e to the RT. So as t becomes larger, this exponential function, e to the RT, will increase without bound, since r was a positive constant. So as t approaches infinity, our population size, y of t, will increase without bound. It is approaching infinity. So we could ask the question then, well, does this seem realistic? Well, no, this is not a very realistic model. Regardless of what population we're talking about, say a human population, some population, say, of squirrels, deer, fish, there can't be an infinite number of that species because we have limitations on space. We can't fit hundreds of billions of people in 1 square foot. So there has to be some maximum sustainable population size based off limitation of resources such as space, food, water, so on. So to answer the second part of this question, we can say no, this does not seem realistic. Since there must be a limit on population size. So this is one drawback of the exponential growth model. It is not a very realistic model if we're looking at predicting future populations over a longer period of time. And in our next section, we're going to talk about some more realistic population models which have a limiting population size. But to consider an application of this exponential growth model, let's look at the following example. So we're told here that a bacterial culture starts with 1,000 bacteria, and after 2 hours, there are 2,500 bacteria. So in part A, we are supposed to find an expression for the population size after t hours, where time t is non-negative. And really, I should say something in the statement of this problem to indicate that we are assuming exponential growth. So let me add a little statement here. Assume exponential growth. For most problems involving the growth of bacteria over a period of just a few hours, the exponential growth model is a reasonable assumption because we're not predicting future populations over a long period of time. If we're looking at only a period of a few hours, then this exponential growth model is not so bad. So for part A, we had found in our previous example that the exponential growth model, or the solution of the exponential growth model, is given by y of t equals y naught, the initial population size, times e to the rt power. Now here, the initial population size, y naught, we were told is 1,000. This bacterial culture starts with 1,000 bacteria. So at any time, our population size, or the number of bacteria in this culture, would be given by 1,000 times e to the rt. And the question is, well, what is this intrinsic growth rate r? Now, to find that, we're going to use the additional information that we're given in the problem statement, that after 2 hours, we have 2,500 bacteria. So we're going to use that to solve for r. So let's take our population size, which was 1,000 e to the rt, and at, well, let me maybe write this out in a slightly different way. So using what we're given, the population size y at time t equals 2, that is after 2 hours, is given by 1,000 times e to the 2r, and we're told that that equals 2,500. So let's see if we can solve for r. We have e to the 2r power is equal to 2,500 divided by 1,000, which would give us 2.5, or 5 halves if we prefer. So to solve for r, we could take the natural log of both sides, and we have 2r is equal to the natural log of 2.5, or I'm going to rewrite that as 5 halves. And so r is equal to 1/2 of the natural log of 5 halves, or natural log 2.5 if you prefer. So once we have this value for r, we can take that value and substitute back into the general expression that we had for our population size y of t. So we find that y of t is given by 1,000 times e to the r, which was 1/2 the natural log of 5 halves t. All right, so this would be our population size at any given time where t is being measured in hours. Now in part B of this example, we're asked to find the population size then after 6 hours. So to find our population size after 6 hours, we would take the function that we just found in part A for the population size after t hours and substitute 6 in for t. So that would give us 1,000 times e to the 1/2 natural log of 5 halves times t, which is 6. So simplifying, we have 1,000 times e raised to, well, our 1/2 times 6 gives us 3 times the natural log of 5 halves. So using a calculator to approximate this value, let's see what we have. So the natural log of 5/2, or 2.5, times 3. And then we are exponentiating that expression. So that would give us a value and then times 1,000. That would give us a value of 15,625. And this is actually an exact value, not even an approximation here. So after 6 hours, we have a population of 15,625 bacteria. And then the question is, in part C, how long would it take the population size to reach a certain value, say 5,000? Now, since we started with an initial population of 1,000, we're asking, well, how long would it take for the population size to reach 5 times its initial value? So to find that time, we would take our function y of t, which represents the population size at any time. So that was 1,000 times e to the 1/2 natural log of 5/2 t, and set this equal to the desired population size, 5,000. And we're going to solve for t. So dividing both sides of this equation by 1,000, we have e to the 1/2 natural log of 5/2 t is equal to 5,000 over 1,000, or 5. And then taking the natural log of both sides, we have 1/2 the natural log of 5/2 t is equal to the natural log of 5. So to solve for t, I would multiply both sides of this equation by 2, and then divide both sides of the equation by the natural log of 5/2. So I have t is given by twice the natural log of 5 over the natural log of 5/2. So using a calculator to approximate this value, let's see what we have. Log of 5 times 2, and then we would be dividing by the natural log of 5/2, which gives us a value of t equals approximately 3.5. And here, let's recall that t was being measured in hours. So after approximately 3.5 hours, we will have a population of 5,000. Now, typically for these types of problems, we can see if our answer makes some sort of reasonable sense. So here we started with a population of 1,000. After 2 hours, our population had more than doubled. We had a population size of 2,500, so certainly to reach a population of 5,000, it should take longer than 2 hours. And we found in part B of the problem that after 6 hours, the population size was 15,625. So the time that we're looking for in part C should be somewhere between 2 hours and 6 hours, which makes our answer seem reasonable here. Now, in the second part of this section, we're going to talk about the exponential decay model, which is very similar, in fact, almost identical to the exponential growth model. And this is usually used to model the mass of some radioactive substance which is decaying over time. So let's suppose that y of t will denote the mass of some radioactive substance at a given time t, which is non-negative. So for the exponential decay model, we will assume that the mass is changing at a rate proportional to the amount of material present, or the current mass. So that is the rate of change of y, our mass with respect to t, is given by negative k times y, some constant multiple of the current mass y, where k is a positive constant called the decay rate of this substance. And we have an initial condition, y of 0 is equal to y naught, which is some non-negative constant, which would be the initial mass of our substance, how much of this radioactive material we started with. So in part A of this problem, we're supposed to solve this exponential decay model, and we can see that it's almost identical to the exponential growth model. The only difference is that the constant r for the exponential growth model is replaced by a constant negative k. So let's go about solving this in the same way. Using separation of variables, I could rewrite my differential equation as dy over y is equal to negative k dt. And then integrating on both sides, we would have the natural log of absolute value y is equal to negative kt plus some constant c. So exponentiating on both sides, I would have the absolute value of y is e to the negative kt plus c power, or as we did for the exponential growth model, we could rewrite this as e to the c times e to the negative kt, where this e raised to an arbitrary constant term is a new arbitrary constant, which we would just call c. So to eliminate the absolute value, we would say y of t could be positive or negative c, e to the negative kt. But again, the positive or negative of an arbitrary constant is still just an arbitrary constant. So let's write this more simply as c times e to the negative kt. Now we need to find the constant c that satisfies the initial condition that we were given, which is y of 0 is some value y naught, which represents the initial mass. So applying this initial condition, y at time 0 would be equal to c times e to the 0, or just c, and we're given that y of 0 is this constant y naught. So substituting y naught back into our general solution, we have y of t is equal to y naught times e to the negative kt power. So the solution of this exponential decay model is exactly the same as the solution of the exponential growth model, where the only difference is that our constant r is replaced by this constant negative k, exactly as we saw in the differential equation. So in part B, we are asked to determine the limiting behavior of a sample as t approaches infinity. So after a long period of time, as time goes on forever, the limiting value of our mass, y of t, of the substance is given by the limit of y naught times e to the negative kt. And for this exponential, e to the negative kt, well, since our exponent for this function is negative, as t increases, the value of this function decreases to 0. So that is over a long enough period of time, our mass will decay to nothing. We will be left with no more of this radioactive substance. So as an example of this exponential decay model, let's look at the following problem. We're told that the half-life of carbon-14, which is denoted as C14, is 5,730 years. So recall the half-life here is the time it takes for a substance to decay to half of its starting value. And we're told that a sample of carbon-14 has an initial mass of 20 micrograms. So in part A of this formula, or this example, we're asked to find a formula for the mass of carbon-14 remaining after T years. So here we're looking at some radioactive substance, carbon-14, whose half-life is known. It's decaying over time. So we're looking at an exponential decay problem. Now, based off what we saw from the previous example, the solution of the exponential decay model is given by y of t equals y naught times e to the negative kt, where y naught was the initial mass of our material. In this case, we were told our initial mass is 20 micrograms. So we have y of t is equal to 20 times e to the negative kt micrograms. And we need to determine what is this decay rate, K, for this particular radioactive substance. Now, to find that, we're going to use the information that we're given about its half-life. The half-life of this substance is 5,730 years. Which means that if we look at our function y of t, which represents the mass, at time 5,730, we would have 20 times e to the negative 5730k. And since that was the half-life of this substance, and we started with 20 micrograms, after this period of time, we will be left with half of what we started with, 10 micrograms. So we can now solve this equation for K. If I divide both sides of my equation by 20, I would have e to the negative 5730k is equal to 10 over 20, or 1/2. And in order to eliminate, well, there's a few ways I could solve here. My personal preference would be to try to eliminate the negative in this exponential. So recall that e raised to a negative power is the same as 1 over e raised to that positive power. So if I were to take the reciprocal of both sides of this equation, I would have e raised to the positive 5730k is equal to 2. And now to eliminate the exponential, I could take the natural log of both sides, and I would have 5730k is equal to the natural log of 2. And so k would be the natural log of 2 over 5730. So this value of k would be my decay rate. And once I have this value for k, I'm going to take it and substitute back into my expression for y of t. So we have y of t is given by 20 times e to the negative k, which was natural log of 2 over 5730 t, where this was being measured in micrograms So we found our formula for the mass remaining after t years. Now, once we have this, we can answer other questions, such as in part B, what is the mass that would remain after 1,000 years? So to find that value, we would look at y of t, which represents our mass, when t is equal to 1,000. And we would have a value of 20 times e to the negative natural log of 2 over 5730 times 1,000. Now, using a calculator to approximate this value, let's see what we have. So we would have our 1,000 over 5730 times the natural log of 2. And then we're taking the negative of that value and exponentiating that expression. And then multiplying by a constant 20, which gives us an approximate value of 17.7, where again this was being measured in micrograms. All right. Now, in part C, we are asked when would the mass be reduced to 15 micrograms. So to determine that, we would take our expression y of t for the mass at any given time, which is 20 e to the negative natural log 2 over 5730 t, and we would set this equal to the desired mass at 15 micrograms. And now we can solve for t. Dividing both sides of our equation through by 20, we would have e to the negative natural log of 2 over 5730 t is equal to 15 over 20, or 3/4. And then taking the natural log of both sides, or perhaps, as I did in the first part of this question, I might eliminate the negative in this exponential by recalling that e raised to a negative power is the same as 1 over e raised to that positive power. So if I want to eliminate the negative in the exponential first, I could take the reciprocal of both sides of this equation, and I would have e raised to the positive natural log of 2 over 5730 t is equal to 4/3. So now, to eliminate the exponential, I could take the natural log of both sides, and I would have the natural log of 2 over 5730 t is equal to the natural log of 4/3. So to solve for t, I would multiply both sides of my equation by 5730 and then divide through by the natural log of 2. So this would be the exact time it takes to reach a mass of 15 micrograms. But for practical purposes, we might want to approximate this value, say, to the nearest hour or the nearest year. So let's see what we have. So we were taking 5730 times the natural log of 4/3, and then we were dividing that quantity by the natural log of 2, which gives us an approximate value of 2,378 years. All right. Now we want to check that this might make reasonable sense in relation to our problem. We know that the half-life of this material is 5,730 years. That is the time it would take to reduce from our 20 micrograms to 10 micrograms. So the time that it would take to get to 15 micrograms should be shorter than that 5,730 years, which it is. And we found that the mass remaining after 1,000 years was 17.7 micrograms in part B. So the time it would take to reduce to fewer than 17.7 micrograms in part C, we're considering 15 micrograms, should be longer than that 1,000 years, which indeed it is. So our answer seems to be reasonable here. So in this section, we've introduced the exponential growth and exponential decay models, which are almost identical. They're just used in different applications. So exponential growth is usually used to model the growth of a population over a short period of time. One limitation of that model is that it is not very realistic in predicting long-term population size. And the exponential decay model is typically used to model the decay of some radioactive substance over time. And it can be used for problems on carbon dating.